All right, 7 o'clock. So we're going to go ahead and get started. So today we're going to be talking about some more Taylor series expansions and some applications that we can use Taylor series for. And then later on, we're going to start to try to get into parametric curves, chapter 9, and we'll talk about that a little bit at the end. So right now I have the warm-up problem. We're going to show that the limit as x approaches infinity of e to the x minus 1 minus x all over x squared is equal to 1/2. And we're going to do that in two different ways. So, of course, you could probably do something that we've learned in previous chapters, or even Calc 1 to do these kind of limits, and then more recent material to kind of figure out what these limits are. So go ahead and see if you can figure out two ways to show that this is 1/2, and then we'll start diving into some of the new material. Okay, so the first way that I'm going to show that this limit is equal to 1/2 is I'm going to go ahead and L'Hopital it. So we notice that plugging in x here for 0, e to the x is going to be 1, we're subtracting 1, and then we're subtracting 0. So it looks like we've got something that behaves like 0 on the top and then 0 on the bottom. So we have an indeterminate form. So we can go ahead and L'Hopital it. So the first way, this limit is going to be equal, after I L'Hopital it, to e to the x minus 1, and then 2x on the bottom, so the derivative at the top and the derivative at the bottom. I can go ahead and L'Hopital this again because we notice it's the same indeterminate form. So we've got the limit as x approaches 0, e to the x over 2. Now, just taking the limit of this is fine, and this is going to be equal to 1/2. So another way of doing this problem is to actually plug in the power series for e to the x. So if we do that, we're going to have that the limit as x approaches 0, and here I'm going to start listing some terms for the power series. So we have 1 plus x squared over 2 plus x cubed over 6. And if you remember, the Taylor series expansion for e to the x is x to the n over n factorial. So now we've got a -1 minus x And then this is all over x squared. Now notice here that we've got this 1, and then we're subtracting this 1 later on. And then we've got this x term in here, and then we're subtracting an x. So these terms are going to be canceling. So we're left with something that behaves like x squared over 2 plus x cubed over 6, and then so on, and this is all over x squared. Now, of course, this is just a polynomial, and if we're dividing by x squared, then we can rewrite this as 1/2 plus x over 6. And then the next term would be, we would have x to the 4th over 24 up there. So once we get rid of that x squared, we're left with another x squared over 24, and then so on. So because power series are continuous functions, we can go ahead and put that limit through, and all of these powers of x and higher are all going to go to 0. So we're going to be left with that 1/2. So this is equal to 1/2. And there we've showed that the limit is 1/2 two different ways. So why don't we look at our next example, which is an integral problem, an integral of sine of x over x dx. So take a few minutes, start to look at this problem. Of course, we're doing power series related stuff. So if you remember the Taylor series expansion of sine, go ahead and use that. There are a few listed functions that you can use for the power series, they're Taylor series expansions. Sine is one of them. So don't feel like you have to find sine all over again. The one listed in the book is centered at a equals 0. That's perfectly fine. So go ahead, take a few minutes, work on the problem, and then we're going to talk about it. Okay, so first off, let's list sine of x over x as a power series. We have 1 over x. Let's sub in the power series for sine. So 0 to infinity, -1 to the n, x 2n plus 1, all over 2n plus 1 factorial. So now we're going to bring the x inside the sum. And this leaves us with -1 to the n, and then x to the 2n, all over 2n plus 1 factorial. So now, what we need to be doing is taking the integral of this power series. Let's go ahead and rewrite that. And now we know how to do this. So we're going to have a big constant c. And our sum goes from 0 to infinity. We're going to have a -1 to the n. We have x to 2n plus 1. And this is going to be over 2n plus 1, and then 2n plus 1 factorial. Right? And this is our power series for this integral. So notice that we can't solve for c because we have an indefinite integral, so we don't have any function to relate it to because it always differs by a constant. So of course this is our integration constant. I can't solve for it, and so this is going to be our final form. So let's go on to number 3 here, and what we're going to be doing is a little bit different, and so we're going to be finding the 3 first terms, I should say non-zero terms, first 3 non-zero terms for e to the x times cosine of x. And we're going to center it at a equals 0. So Maclaurin series. So go ahead and take a few minutes. There's a few ways you can do this problem. So pick one and figure out the first 3 non-zero terms, and then we're going to talk about it in just a bit. Okay, so we have this product of e to the x and cosine of x. Now, you could go ahead and take the derivatives of these and find the nth derivative, or because we're looking at the first 3 non-zero terms, take a finite number of derivatives. You don't really have to figure out a pattern then, and then plug those into our Taylor series expansion when we have the derivatives and at a equals 0. But I'm not going to do that. What I'm going to do is a little bit different. So I notice that we've got e to the x cosine of x. And what I'm going to do is I'm going to plug in a Taylor series expansion for e to the x. And then So this keeps going. Then I'm going to have the cosine power series here. And what I notice is that these are, of course, products, and these are polynomials that span, like just keep going, right? They're infinite polynomials. But what I can do is recognize that this one is going to multiply each one of these forever. This x is going to do the same thing. It's going to get multiplied by all of those terms forever. This term, and so on. So what I'm going to do is first I'm going to write 1 times 1 minus x squared over 2 plus x to the 4th over 24, and so on. Well, this is just, because we're multiplying by 1, the same thing. And so on. Then I'm going to take this x and multiply it through. And this comes out to being, so we're raising the power of everything. And then this x squared over 2 term. So multiply this out, you get an x squared over 2 minus x to the 4th over 4, then plus x to the 6th over 48, and then so on. Now we've got this term. Now, we'll notice that, remember, I'm only looking for the first 3 non-zero terms. So these real high powers, like this 6th power, I'm probably not going to use them, right? So I'm only going to be worrying about it multiplied on this x squared term. And that gives me an x cubed over 6, then an x to the 5th over 12, so on. And then the last one I'm going to have is this x to the 4th, just in case. And then I'm not going to worry about these higher terms here. And this is just going to be x to the 4th over 24, and then a bunch of other higher order terms. So if I have this grouping now, all I need to do is just add them together and collect terms. So I'll notice, should use a highlighter here. So this one is the only constant term that I have. So I'm going to have a +1 here. Now, let's look at the x squared, or just the linear terms. I have this, and there doesn't appear to be any other linear terms, so we have x here. Now, what about x squared terms? Well, I've got an x squared here, and I've got an x squared here. Oops. There we go. X squared there. And then remember that this one's a minus and this one's a plus. So what ends up happening is I have something like that. But that's going to be 0. So I can't really use that in my first 3 non-zero terms. So I'm going to have to go a little bit further here. So why don't we look at the cubic terms. And I've got these two. So we've got plus 1/6 minus 1/2 x cubed. That was the yellow. Why don't we go ahead and start adding the fourth terms. Got some fourth terms here. Bunch of these fourth terms. Oh, actually, I'm sorry. We have this one and this one. For some reason, this fourth here should be a fifth, right? Because it was fourth before, and then we multiplied it by an x. So that's a fifth term. So we only have those 3 1/4ths, or the x to the fourths. So this is 1/24 plus 1/24 and minus 1/4 x to the fourth, and so on. So it has some extra terms, but we don't really need to worry about those. So this is going to be 1 minus or plus x. Then we're going to have minus x cubed over 3, and then minus x to the fourth over 6. So we actually really didn't need this x to the fourth term because we have these 3 terms here, but we were just being safe because we didn't know like this x squared term was a 0 term. So we just went a little bit higher just to make sure that we were okay. Like if this had been, these coefficients were 0, then we would have needed this x to the fourth term. So our final answer is just that right there. 1 plus x minus x cubed over 3. Okay. So that brings us to our fourth example. So we're going to have a lot of examples in this recitation until we get to some of the parametric stuff. We are going to talk about a few brief things, but most of the time it's just going to be explanations of Taylor series and examples, because that's what applications are, right? Applying it. So let's do a different kind of problem. Finding out what sums are equal to. So we've got this sum from 0 to infinity of 1 over n factorial. What is this equal to? And then for b, let's write it out a different kind of way. So we have 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, and so on. What is this equal to? So go ahead, take a few minutes, and then we're going to talk about them. Okay, so these are pretty brief examples. Let's look at A here. So we've got this 1 over n factorial. So let's look back and what power series might resemble this. So if we can recall anything that takes the form of something that we can get to 1 over n factorial, then if we know that corresponding power series, then we can just plug in 1. Well, if we had something like n 0 to infinity of some kind of maybe function of x, let's write the function of x here, that comes out to being 1 when we input it. So we have to put in something and get 1. Then we have over n factorial. Well, what if we just had x to the n? And of course, this power series is just e to the x, right? So my power series, or I shouldn't say power series anymore, if we input just a number. So this guy is when x is 1, right? So that means that if we just put in 1 into our function that resembles, so e to the first, that's just e, right? So this sum goes to e, an irrational number, which we've kind of seen before with different types of sums. Pretty interesting. So let's go ahead and look at b now with the same kind of idea. We have that this 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, right? Well, is there some kind of power series that resembles this? Well, we do have x minus x over 2 plus x over 3 minus x over 4 plus x over 5, and so on. This was equal to our natural log of 1 plus x, right? So we know that 1 minus 1/2 plus 1/3 minus 1 over 4 plus 1 over 5, and so on. That's just the natural log of 2 when we input 1 for x. Right? So this is another way that power series are useful, is actually finding out the sums of things that kind of resemble it. So let's do another limit problem. So we've got the limit as x approaches 0, sine of x minus x all over x cubed. Okay. So let's go ahead and try doing a power series method to try to figure out what this limit is. It's pretty easy. And then we're going to talk about some other things. So go ahead, take a few minutes, work on the problem, and we'll talk about it in just a bit. Okay, so let's input the power series for sine of x into this limit. So we've got x minus x to the third over 3 factorial plus x to the fifth 5 factorial, and so on. We're subtracting an x in the numerator, and then this is all being divided by x cubed. Well, we notice that the x here and here, these two x's are going to cancel, and then we're dividing everything by x cubed. So all of these powers go down by 3. So we've got the limit as x goes to 0, negative 1 over 3 factorial. And then we're adding an x squared over 5 factorial. And then we'll just include the next term here, just so we're okay. And of course, all of the higher powers are going to have x's in them. So when x goes to 0, all of these other terms are going to be going to 0 here. So those are all going to 0. And then we're just left with this is equal to negative 1/6. So take a little break there, and then we're going to be talking about something that, very briefly, that we've learned a long time ago. So if we look at the very first Taylor series expansion, so T1, right? We have that it's f of a plus f prime of a times x minus a, right? Well, this might look familiar from something that we learned in Calc 1. If you remember, the book defines it as L of x, right? This means that we have this L of x equals f of a plus f prime of a times x minus a. Well, this was the linearization that we learned back in Calc 1, right? Because we are approximating a function with its first order Taylor series expansion, meaning that we're taking a linear approximation of it. So that's where linearization comes from. So that's something that we learned a little bit back in the day, right? So another thing with power series is, how do we calculate something like this, right? We have got some kind of a plus b to some kind of power. Once we're all done foiling, what is it going to look like? Well, we can write this as a finite sum as long as n is a positive integer, right? We have I equals 0 to n, and then we have these binomial coefficients. We'll talk about that in just a second. And it's a to the n minus I, and then b to I. So defining what these coefficients are, this is going to be n times n minus 1 times n minus 2. We're going to keep multiplying until we get to n minus I plus 1. And this is all going to be over I factorial. And we're just going to assign the quantity that n 0 is equal to 1. So this helps us find, like, foiling things out. And of course, it's not an infinite sum, so we're going to get to that in just a second. But this does help us look at these FOILed out terms. Right? So now, if we've got something like this, well, we can define it using a power series. 0 to infinity, and then we'll have kn x to the n. So k doesn't necessarily need to be an integer here, nor does it need to be positive. So let's look at a special case where we want to expand this. We've got the square root of 9 minus x. So work on it a little bit. So you can immediately try to get to the power series by our definition up here. So go ahead and see if you can find the first few terms. I wouldn't suggest going higher than the squared term. In the example, we're going to go to the cubic term, so no worries there. But go ahead, write out what the power series of this is going to be, and then find the first few terms. Okay, so we have the square root of 9 minus x. Well, let's kind of rewrite this. If I factor out a 3 here, I'm going to get the square root 1 plus minus x over 9. And this helps us because now we've got it in the form with this 1 plus x, this quantity x, raised to some k power. Well, in this case, k is 1/2. So, sorry about that. I'm back a few pages. Okay, here we go. So, we can write this as equal to 3 times the quantity, the sum here, from 0 to infinity. I have 1/2 here and here. And then we have minus x over 9. This is raised to the power m. So we're going to write the first few terms out here. 3 quantity, and then the first term we're going to get out of this is 1. Then we're going to have 1/2 negative x over 9. Next one is this 1/2 times negative 1/2 over 2. And this is negative x over 9 squared. And then this next term is 1/2 minus 1/2 minus 3/2 over 6. And then we're going to have a minus x over 9 cubed. And then so on. This comes out to being 3 minus x over 6 minus x squared over 216. This is why I shouldn't really go higher than the squared term. So we have x cubed over 3,888. So that's not something they can really do in their head. So don't worry about going that far with it. Most of the time will probably be a lot simpler. So that brings us to parametric curves and how to really deal with these. So what does it really mean? So let's start off with an idea. We've got x squared plus y squared equals r squared. Everyone looks at that and they recognize that it's the equation for a circle, right? So we've got some kind of circle here, and we know that this equation describes some point on this line where we've got that this radius is r, right? So we can write that in terms of y and x. So we got y equals plus or minus the square root of r squared minus x squared, or we can write x equals plus or minus the square root of r squared minus y squared. Well, if we look at this first equation, we've got a plus here and a minus here. What does the plus represent and what does the minus represent on this circle? Well, if we go back to our circle, this minus is only going to be talking about the lower half of this circle. And this is only going to be talking about the top half of the circle. So that's not very helpful because we would always like to think about the circle as a whole instead of these halves, right? Because otherwise it's not a function. It doesn't pass the vertical line test. And if you look at it in terms of x, then you don't pass the horizontal line test, so to speak. And so the circle is not really a function in terms of this x and y as we have them. So is there some way to describe it in a sense that's more fluent, more continuous? So what if we could possibly write that x is equal to some function, and then y is equal to some function? Let's kind of make the y's and g's look a little bit different there. There we go. So we're going to make it a function of t. Now you can think of t as some kind of time parameter, although our circle is not moving at all. What we can do is let's think about a point on the circle, and we'll give it some kind of time dimension where as we increment time, its point slowly moves around. So let's draw a bigger circle here and kind of talk about what that means. So we've got a big circle here. Maybe I'm somewhere over here, and I want to move this way on the circle until I get to some point here, and then I can keep going around in the circle I go. So I can describe points on this circle with these functions f of t, g of t. So what are f of t and g of t? Well, they're called parametric equations. And to kind of get a sense of how they really work, let's look at an example that's a little bit easier. Let's first look at parametric equations that are already predefined. So we have x equals t squared plus t. And we'll look at y equals 2t minus 1. And we'll specify that t goes between -1 and 1. Okay. What does this describe? So one way of really doing this is to build a little chart, plug in values of t and see what happens. So let's go ahead and do that. We've got t, x, and y. Let's plug in our endpoint, right? -1, the first point that we have. Well, if we plug -1 into our x equation, we are going to get 1 minus 1, so we're going to get a 0 there, right? And here for the y term, we're going to get a -3. Now let's look at 1/2. We're going to get a -1/4. Then we're going to get a -2 here, 0. And then let's just do increments of 1/2. So at 0, we're going to have 0 here, and -1. Then we're going to have 3/4, 0, and then 2, 1 here. So let's go ahead and plot this. So with our very first point, 0, -3, we're somewhere down here. And then we come up 1 unit, move a little bit off to the side. Then we come back to the y-axis. Then we're going to be just on the x-axis. And then we're going to come off of it. So the parametric equation kind of looks something like this. And I shouldn't really draw an arrow there because we stop at 1. So it's also worth noting that it moves in this direction. So you can put little arrows there just to indicate which direction this point is moving. If you like to think about it as a particle, that's perfectly fine. So as this particle is moving, you can denote it with these arrows. So let's go back and talk about our circles here that we were talking about at the beginning. Well, that's font's real big. All right, so what can x be? What I mean by this is what values can x take? Well, let's kind of look at a special case. Let's pick that r equals 1, right? So we're looking at the equation that x squared plus y squared is equal to 1, right? And if we look at our circle, let's draw a circle out to the side here. It's kind of an oval. Let's do circle. Try to get it centered right. All right, that's good enough. So if we look at, you know what, I'm going to actually draw this a little bit bigger. So I'm going to do some diagrams inside of it. So we've got there we go. So let's start off over here. And we're going to call this t equals 0. That's way too. This is t equals 0 over here, right? And some point that we're going to get to later, we're going to say that this is t equals t1. Well, we need something that defines the x coordinate and y coordinate of this. So the x coordinate is how far that's across. And then the y coordinate comes down like this. Now, is there some kind of function that describes this? Well, remember that x, now because we're looking at the circle of radius 1, x is going to be no smaller than -1, no bigger than 1. And the same goes for y. Y is going to exist somewhere between -1 and 1. So given a certain point on this curve, we need to define its x and y coordinate. Well, luckily for us, there's functions that actually do exactly that thing. The trig functions, cosine and sine. So if we're starting at t equals 0, then we're going to want x to being equal to cosine of t. So when t is 0, this gives us 1. And when we define y as sine of t, then we have that at time equals 0, we've got 0, right? And as we're moving time, we're going around this unit circle. So how about we have that I want a circle with the center at hk and a radius of r. So looking at my parametric equation for just the circle of radius 1, let's look at a circle first off that has a radius r, so arbitrary radius. Well, it's not too hard to believe that if we have a circle, let's go back to our circle over on the right, that if this is now a circle of radius r, let's go ahead and draw that. So that's radius r. So this here, this is the x component, right? That would simply be, if this was the unit circle, this would just be cosine. But because we're looking at r, this is going to be r times cosine. Right? So our x here is going to be r times cosine of t, and y is equal to r sine of t. Now that's only for a circle that's still at the origin. Now, if we wanted to move our circle of radius r somewhere else, so we've got something like this. Well, here in the middle, there in the middle, we've got hk, right? And if we wanted to look at the x coordinate, right, and the y coordinate, well, this x here is defined by our r cosine t. But now we're moved over an amount that happens to be this right here, which is h. So it makes sense that we can define this as r times cosine of t plus h, and then y is equal to r times sine of t plus k. And that's a way to define our parametric equation for a circle centered around hk of radius r. So parametric equations seem pretty simple when you first start off, right? Like, this wasn't that big of a deal. Make sure that you understand this, though. It's not too far off, describing like some kind of particle that's moving along a curve, and that's how you're going to define the x and y coordinate. You're going to start talking about the slopes of these things. How does x change with time, and how does y change with time, and how does that mean that y changes with x if you know how x depends on time and how y depends on time. So you're going to get into a little bit more on that. You're going to start learning about how to characterize points that are not simply just x and y coordinates. There's other ways of defining coordinate systems, not just up and down, left and right, but rather like you're going to be learning about polar coordinates, for example, which means that you start at some point. Let's take our circle, for example, this big point here in orange. Well, its coordinate is specified by an angle and then how far you go away from the origin. That's polar coordinates, and you're going to be learning about that. So feel strong about parametric equations. They're gonna show up. So with your exam next week, make sure you feel confident with this parametric stuff right now, and the power series, Taylor series expansions. I feel like that's the hardest test. Really know your stuff for power series. Right? If you have any questions, make sure you email either Dr. Chang or me. And this will be my last recitation. So I hope you guys do well with the rest of the course. You can send me emails by the end of the week. I suggest you do so if you've got any questions. So other than that, take care. Hope to see you guys in higher level math classes. I might be teaching those, so go ahead, study up, and I will see you guys in Calc 3.